grow it habit.
Okay, let's be honest. When you think about the ground beneath your feet, what's the first word that pops into your head? For most of us, right, it's probably just dirt. You know, something simple, something you wash off your shoes. Well, we're about to totally flip that idea on its head.
So let's just start with this. What if that stuff we call dirt is actually the most important thing on Earth? I mean, what if this thing we just walk all over is one of the most complex, most vital systems on our entire planet? That's exactly what we're going to dig into today.
All right, so before we even get into the nitty-gritty of what soil is, we got to talk about why you should even care. Because it's so much more than just the stuff holding up our houses. It's literally the foundation of life as we know it.
I mean, think about it. Understanding soil isn't just for scientists in a lab. It's super practical. It's how farmers can get the best possible crops from their land, and that leads to healthier soil, which is the absolute key to sustainable farming. And you know what happens when soil is healthy? We don't need to dump as many chemical fertilizers on it. It's this incredible domino effect, and it all starts with the ground.
Okay, so we get it. It's important, but what is it, really? Let's peel back the layers and get past that simple word dirt and see what's actually going on. It's a whole complex system.
You know, it's kind of funny. The word soil actually comes from the Latin word solum. And you know what that means? Just floor. And for hundreds of years, that's pretty much how we thought of it, just the floor of the world. But now we know, oh boy, the real story is so much more interesting.
And this is the modern definition. It completely changes the game. You got to focus on these words: dynamic, natural body, and living forms. Dynamic means it's always changing. It's not static. Natural body means it's not just a random pile of rocks and sand. It has structure. It's organized. And maybe the most important part, living forms? Soil is literally alive. It's a teeming ecosystem.
So even scientists look at soil in two totally different ways. It's kind of like you can study a forest just to understand how a forest works, right? Or you could study a forest to figure out the best way to harvest wood. Two different goals, but both are super important for understanding the whole picture. So yeah, it's all about your point of view. On one hand, you've got pedology. Think of these guys as the soil biologists. They're fascinated by the soil itself. They ask questions like, where did you come from? What's your story? Then you have edaphology. These are the soil engineers, or maybe the farmer's best friends. They're all about how plants see the soil. Their big question is, how can we use this soil to grow bigger, better, healthier plants? So one is pure science, the other is applied science. And those two big ideas, studying soil for its own sake and studying it for what it can do, they're the building blocks for the whole field of soil science. And that field gets broken down even more, into 6 key areas. So, what is soil science? Big picture. Well, it's the branch of science that looks at soil as what it is, a natural resource. A really, really precious one, right up there with clean air and fresh water. So first up, we have our old friend, pedology. We just talked about this one. This is really the foundation. These are the people who are like soil genealogists, right? They're figuring out where each soil came from, what its personality is, and mapping out where it's found all over the world. Then we've got soil physics. This is all about the physical stuff, the texture, the structure. Is the soil heavy and dense like a lump of clay, or is it light and sandy? These physical properties are a huge deal. They control everything from how quickly water soaks in to whether a tiny little root can even push its way through. After physics comes soil chemistry. And man, this is where it gets busy. There is a whole universe of chemical reactions happening down there all the time. This is where we look at the nutrients, the acidity, the pH, and all the little chemical handshakes that happen to make food available for plants.
And that leads us right into soil fertility. This is where the chemistry gets really fast. This is the discipline that answers the big question for every farmer. Does my soil have what it takes to grow food? It's all about checking the nutrient levels to see if you can grow healthy crops.
Okay, now we get to what I think is the coolest one, soil microbiology. Remember that living forms part of the definition? This is it. We're talking about the billions, with a B, of bacteria, fungi, and all sorts of other tiny critters in just a single handful of soil. They're the cleanup crew and the recycling plant of the natural world. And last but not least, we have soil conservation. This is the one that looks to the future. It's the discipline that asks the really tough questions like, how do we keep feeding a growing world without totally wrecking this resource? It's all about keeping our soil safe from being washed or blown away so our kids and grandkids can use it too. So, all this amazing, complex science, You might think we've known it forever, but no way. This is all pretty new stuff. I mean, for most of human history, dirt was just, well, dirt. Let's take a quick look at how we figured all this out. You know, for a really long time, we were completely on the wrong track. Back in the 1600s, this one experiment made everyone think plants were basically just made of water. It took until the 1850s for us to finally prove, no, plants are getting essential stuff like nitrogen from the soil. But the big aha moment, that came in the 1870s from a Russian scientist named Dukachev. He was the first person to stand up and say, hey, everybody, soil isn't just a pile of crushed rock, it's a natural body. And that one idea, that changed everything. It's the foundation of all modern soil science, all the way to the complex math we use today.
Which brings us right back to this quote. This might just be the most important sentence ever written about soil. Soil is a natural body. So simple, right? But with those 4 words, Dokuchalov took dirt and turned it into a complex, fascinating system that deserved its own field of science.
So there you have it. We've journeyed from simple dirt to Solemn, the floor, all the way to a dynamic, living, breathing ecosystem. We know what it's made of, how it works, and just how alive it really is. The science is all there. So I guess the only question left for all of us is, now that we know all this, what are we going to do about it? How are we going to treat this incredible resource that's right under our feet?
Have you ever really stopped to think about what's right under our feet? I mean, it seems so simple, right? It's just dirt. But the ground beneath us is actually this incredibly complex, living world. And it's telling a story that goes back thousands, even millions of years. And what if I told you that scientists have a universal language to read that story? Trust me, it's way more fascinating than it sounds.
So let's kick things off with a really basic question. What's the deal with dirt versus soil? To most of us, they're pretty much the same thing. You know, dirt is just what you wash off your hands or sweep off the floor. But to a scientist, the difference is absolutely everything.
You see, soil isn't just some random stuff. It's this dynamic, natural body that has a past, a present, and a future. And to really get a handle on it, scientists had to create a universal language, a global system to classify every single type of soil on Earth. And in this explainer, we're going to learn how to speak that language.
Okay, so think about it. The world has an incredible diversity of soils. How do you even begin to organize all of that? Well, scientists came up with a solution. It's called soil taxonomy, and it's basically our key to cracking the code of the ground we walk on.
The easiest way to think about it is to compare it to how we classify animals. You know, kingdom, phylum, class, all that stuff. Soil taxonomy is a lot like that. It's a system with different levels that organizes soils based on things you can actually see and measure, like its color, its texture, and how its layers, or horizons, are stacked up. This system means a scientist in India can talk about a specific soil, and a scientist in Indiana knows exactly what they're talking about. It's a shared language. And here's how that whole system breaks down. You can see it's a hierarchy, right? It starts out super broad at the top with what's called an order. Then, as you go down the list, it gets more and more specific, through suborder, great group, all the way to series, which is the most detailed, laser-focused level you can get. A series describes a soil with really specific uniform characteristics. So at that highest, broadest level, how many categories do you think there are? You might guess hundreds, but get this. Every single soil on planet Earth, from the frozen ground in the Arctic to the red clays of the tropics, can be classified into just 12 major orders. Only 12. And here they are, the 12 big ones. Now, you don't need to memorize all these names, but soil scientists have this great little mnemonic to remember them: a Vagami house. The key thing to understand is that each of these represents a totally different world. The difference between a Galisol and an Oxisol is literally the difference between a frozen Arctic tundra and a lush tropical rainforest. It all comes down to things like temperature, water, and time. Okay, that's the big global system, but it's kind of abstract, right? Let's bring this down to Earth, literally, and see how it works in the real world. We're going to zoom way in on India, a country with this huge diversity of climates and geology, and see how these soil orders play out on a national scale. And to do that, we're going to put 2 of the country's most important and widespread soil types side by side. You'll see they couldn't be more different, and they actually fall into 2 completely separate soil orders. All right, check this out, because these 2 are like night and day. Over on one side, you have the famous black soils, which belong to the vertisols order. These formed from old volcanic rock, and their special clay, montmorillonite, gives them a superpower. The soil dramatically swells up when it's wet and then shrinks and forms these huge, deep cracks when it's dry. That constant churning action is just perfect for growing cotton. Then on the other side, you've got red soils, which are part of the alphasols order. These come from granite, and their clay, kaolinite, has a much more stable, rigid structure. That means water drains right through them, which makes them less fertile, but also easier to manage. Now let's zoom in even closer. From the national level, we're going to dive into one state in central India, Chhattisgarh. This is where those broad scientific classifications really meet the day-to-day reality of farming. And this chart just tells the story perfectly. You can see right away that the red and yellow soils, which are a type of alphasol, absolutely dominate the state. They cover about 55% of the land. But you've also got big chunks of red sandy soils and, importantly, about 15% of that really fertile black soil, the vertisols we were just talking about. And this, right here, is where it all comes together. Local farmers aren't walking around saying alphasols or vertisols. Of course not. They have local names. That red, yellow soil, they call it Matasi. The less fertile red sandy soil is known as Tikra. And that prized, super fertile black soil, that's Kanhar. Each name is tied to this deep, practical understanding of what the soil can do, how fertile it is, and exactly what crops are going to grow best there. So why does any of this matter? Why go through all the trouble of classifying soil into these complex categories? Well, it's because this system does something amazing. It turns what seems like simple dirt into powerful, actionable data. And this quote from our source material just hits the nail on the head. Remember Ceres, that most specific level of classification we talked about? Well, that's the level people use for making real, on-the-ground decisions, planning out a farm, figuring out where to build, or protecting a specific patch of land. I mean, at the end of the day, this is huge. This system isn't just some academic exercise. It helps farmers pick the right crops, just like we saw with the Kanhar soils in Chhattisgarh being perfect for sugarcane. It helps governments make smart choices about where to build cities and where to protect forests. And it gives us the data we need to predict how soil will behave so we can manage this vital resource for generations to come. So the next time you look down at the ground, remember, it's not just dirt. It's a complex system. It's a living record of our planet's history. And thanks to this global language of soil classification, it's a resource we can finally understand, manage, and hopefully protect. Which really just leaves one last thought. Whether it's sandy or full of clay, whether it's dark or light, every single soil has a history and a purpose. So what story is the soil in your backyard telling?
Hey everyone, and welcome. Today, we are digging deep, literally, into this invisible world right under our feet. We're going to uncover a hidden chemical drama, a real mystery that decides if a plant thrives or, well, starves. And this affects everything, from the little plant on your windowsill to the food that ends up on your plate.
So, I want you to imagine something. Picture yourself as a plant. You're sitting in soil that is just packed, I mean loaded, with all the delicious nutrients you could ever want. But, for some reason, you're still hungry. This is the big mystery we're going to solve today. Think of it as a botanical detective story. And the crime scene? It's the soil itself.
And this is the question that just drives so many gardeners and farmers crazy. It's a total paradox, right? How can a plant be surrounded by a feast and all-you-can-eat buffet and still be unable to get a single bite? The food is there, but it's completely locked away. The real question is, what holds the key?
Well, our first major clue is a fundamental property of soil, something we call soil reaction. You can think of this as the master key that controls whether or not a plant can even get to that underground buffet. If you don't have the right key, all those nutrients might as well not even be there.
So what exactly is soil reaction? The simplest way to think about it is like a snapshot of the soil's chemical personality. You know, is it acidic, kind of like lemon juice? Or is it alkaline, more like baking soda? Or is it sitting somewhere perfectly in the middle, what we call neutral? This one single property, believe it or not, sets the entire stage for everything else that happens down there.
Let's just look at the two extremes for a second. On one hand, you have acidic soils. They've got a whole lot of these things called hydrogen ions, which makes them really reactive. On the other hand, you've got alkaline soils, which have way fewer of those ions. And this balance, it is absolutely critical for a plant's health.
And the universal tool we use to measure whether a soil is acidic or alkaline is the pH scale. I want you to think of soil pH as the main control dial for the entire soil ecosystem. It directly tells you which nutrients are going to be available for the plant to eat and which ones are going to get locked up tight.
But, okay, to really get how pH works its magic, we need to go even deeper. I'm talking down to the microscopic level. We have to meet the real unsung heroes of the soil world, these tiny little gatekeepers that are actually holding on to all the plant food.
All right, say hello to the soil colloids. Now, these are particles that are almost unimaginably small. They're a mix of microscopic mineral clays and broken down organic stuff we call humus. They might be tiny, but their chemical influence is absolutely enormous. They are, by far, the most active and dynamic part of the soil.
You know, the easiest way to picture a soil colloid is as a tiny little magnet. And these magnets have a negative charge. And what do we know about magnets? Opposites attract. So these little negative magnets float around and they grab onto and hold all the positively charged plant nutrients, things like calcium, potassium, and magnesium. And these colloids have some pretty amazing properties. For one, they're microscopic, obviously. Two, they have that negative charge, which is perfect for attracting those positive nutrients. And three, there are billions and billions of them in just a handful of soil. Their combined surface area is just massive, and that's what gives soil its incredible power to store nutrients.
Okay, so we've got our clues. We have the master key, that's the soil's pH, and we have the tiny nutrient magnets, those are the colloids. Now it's time to put these two things together and see how they solve the mystery of our starving plant.
And this brings us to the million-dollar question. If pH is the key that unlocks the nutrients held by our little colloid magnets, then what number on that pH scale opens the door to the biggest, best feast for the plant?
And here is the answer. Look right in that middle, neutral range. See that? Most of the essential nutrients are readily available. It's the sweet spot. But if you go to the extremes, the story completely changes. In really acidic soil, super important things like phosphorus get totally locked up. At the same time, other things like iron can become so available they're actually toxic. And then, in very alkaline soil, things like phosphorus and iron become unavailable all over again. Now, right about now, you're probably thinking, great, I'll just change my soil's pH. But hold on, it's not quite that simple. Soils have something called buffering capacity, which is basically the soil's built-in stubbornness. A soil with a really high buffering capacity, often one that's full of clay and organic matter, is going to fight you tooth and nail to resist any changes you try to make to its pH.
So, now you have the tools, you get the key players, and you understand the chemical drama that's unfolding underground. Now you can look at a struggling plant and know that the problem might not be a lack of food at all, but simply a lack of access to that food.
Let's just do a quick recap of our detective story. It's really a three-step process. First, those tiny colloid magnets hold on to the nutrients. Second, the soil's pH acts like the master key, controlling whether they're locked up or released. And third, hitting that pH sweet spot ensures the plant can finally eat.
So if you remember one thing from all this, let it be this. A soil can be absolutely packed with nutrients, but if the chemistry, specifically the pH, is wrong, those nutrients are basically locked in a chemical prison, completely inaccessible to the plant. And that kind of leaves us with one final thought. The ground we walk on every day isn't just dirt, it's this incredibly complex, living chemical engine. It really makes you wonder, doesn't it? What other invisible dramas, what other locked up treasures are waiting in the soil right beneath your feet?
Have you ever stopped to think about what's really going on right under your feet? I mean, we walk on it every single day, but it's so much more than just dirt. It's this hidden, incredibly complex, and absolutely vital world. And in this explainer, we're going to dig deep, literally, to uncover the invisible forces in the soil that make all life on Earth even possible.
You know, we all see a healthy plant, right? Or a giant tree, a whole field of crops, and we see the results. But what's happening beneath the surface? What is the secret engine that's actually driving all of that life? Well, that is exactly the question we're tackling today.
And the answer, it turns out, all comes down to this really fascinating, delicate balancing act. It's a dynamic dance between three key players: the soil's temperature, the air it breathes, and the water it holds. If you get just one of these wrong, the whole system can just fall apart.
So let's start with our first pillar, temperature. A really good way to think about this is that the soil has its very own microclimate. Yeah,
a hidden world of heat exchange that has this huge impact on everything that tries to grow in it. Okay, so how does soil heat up in the first place? Well, you can think of it like wearing a black t-shirt versus a white one on a really sunny day. It's the same idea. Dark, rough surfaces just soak up way more of the sun's energy, while light, smooth surfaces bounce it right off. The exact same thing happens with soil.
Now, scientists have a name for this, of course. It's called albedo, and it's really just a fancy way of measuring how reflective something is. So, dark soils, they have a low albedo, meaning they soak up more heat. And those light-colored sandy soils, they've got a high albedo. They reflect a lot more of that energy right back into the atmosphere.
But, just absorbing heat is only half the story. The soil also has to move that heat around, right? It needs to get it from that sun-baked surface way down to the cooler layers where all the roots live. And that ability, well, that's called thermal conductivity.
And this is where it gets really interesting because the material itself matters a lot. Just look at this chart. Solid minerals like quartz are fantastic at conducting heat. Water's okay, but look at air. It's an awful conductor. It barely moves heat at all. This shows you perfectly why a wet, packed-down soil, which has way more water and less air, transfers heat so much better than dry, fluffy soil.
And just like soil heats up, it also has to cool down. A huge chunk of solar energy gets used up in this process called evapotranspiration. Basically, that's just water evaporating from the soil and also being released from plants. This whole process has this incredibly powerful cooling effect, kind of like sweating, which keeps the soil from totally overheating on a hot day.
All right, that brings us to our next pillar, air. Now, this might sound a little strange, but soil actually needs to breathe. There's an entire atmosphere trapped down there between all the soil particles, and its chemical makeup is really different from the air that you and I are breathing right now.
Just check out this comparison. The oxygen levels, yeah, they're pretty close. But whoa, look at the carbon dioxide. Soil air has over 6 times more CO2 than our atmosphere. That is a massive difference.
So you got to ask, right? What is going on here? Where is all of that extra CO2 coming from?
Well, it's a direct sign of life. It's as simple as that. Just like us, all the plant roots and the billions of tiny microorganisms living in the soil are constantly breathing. They're taking in oxygen and breathing out carbon dioxide. So that super high CO2 level, that's actually the proof that the soil is a living, breathing ecosystem. Pretty cool.
And that leads us perfectly to our third and final pillar, the one ingredient that honestly connects everything else: water. You can think of it as the lifeblood of the entire soil system. It's the universal solvent, it's the transportation network, it's everything. So, we all remember the water cycle from school, right? Evaporation, condensation, rain, the whole deal. But for the soil, the absolute most important step is that very last one, infiltration. This is the moment water actually leaves the surface and starts its journey underground.
So what is infiltration? All it is the process of water soaking into the soil, seeping down into all those tiny little gaps and channels between the particles. And without good infiltration, rain just runs right off the surface, which causes erosion and leaves the ground totally parched.
Now, once that water gets inside, the soil basically turns into a giant sponge. It holds onto that water, creating this amazing natural reservoir that plants and all those living critters can draw from when things get dry. This ability to hold water is honestly one of the most critical jobs of healthy soil.
Okay, so we have our 3 pillars: temperature, air, and water. But here's the kicker. They don't exist in a vacuum. They are constantly interacting, all the time, in this incredibly delicate, high-stakes balancing act.
And this right here, this is the core of the whole challenge. See, all those tiny little gaps in the soil, the pore spaces, can only hold one of 2 things at a time, either air or water. So they're in this constant competition for the same very limited real estate.
And if that balance gets thrown off, the consequences are severe. Think about it. If a soil gets waterlogged, it's completely full of water. There's zero room for air, and the plant roots literally suffocate. But on the flip side, if it's too dry, sure, there's plenty of air, but the plant dies of thirst. It's a classic catch-22.
So what does that perfect balance actually look like? Well, this is it. This is the ideal recipe for a healthy soil. About half of it is solids, the minerals, and a little bit of organic matter. But look at the other half, that critical pore space. It's split perfectly, 25% water and 25% air. That right there, that is the sweet spot that allows life to absolutely thrive.
Look, understanding this balance isn't just some academic exercise. It matters for everything, from whether your garden succeeds or fails to the entire future of sustainable agriculture. Managing this hidden world is absolutely essential for the health of our ecosystems and for how we manage our most precious resource, water.
So the next time you look at the ground, I hope you remember it's not just dirt. It's a living, breathing system with its own climate, its own atmosphere, and its own water cycle. Which really just leaves us with one final, pretty important question. If this invisible world is so incredibly vital, what happens when we treat it like dirt?
All right, today we're going to dig into a topic that is, well, absolutely fundamental to agriculture and, honestly, our planet's health. We're talking about problematic soils. It's a huge challenge, affecting vast stretches of land all over the globe. But as we'll see, it's one that science is definitely equipped to solve. But to do that, we first have to ask a really big question.
Have you ever wondered about this? I mean, you can see two pieces of land right next to each other. One is just bursting with life, and the other looks, well, dead. The answer, more often than not, is hidden right there beneath our feet, in the actual chemical and physical makeup of the soil itself.
So, here's what we're going to cover. First, we'll look at what happens when good soil goes bad. Then, we'll get into two of the biggest culprits, too much acid and too much salt. And finally, the really hopeful part. We'll explore the incredible science of reclamation, which is all about how we can heal the earth and bring it back to life.
Okay, let's start at the very beginning. What exactly turns a perfectly good, productive piece of land into a problem? It's not just that it's infertile, it's that the soil itself has developed these specific, harmful qualities that are actively fighting against life. And here's the official definition we're working with. A problematic soil is one where natural processes, or let's be honest, sometimes our own activities, have totally changed its basic properties. These changes create a hostile environment that really limits or sometimes even stops plants from growing at all. So the key takeaway here is that these soils need a specific diagnosis before we can even think about a cure. Let's meet our first offender, acidic soil. Now, this is a super widespread issue, kind of a silent threat that can slowly choke the life out of a field without any obvious signs, until it's way too late. So what's the big deal with a low pH? Well, it's like a two-pronged attack on plants. First, it locks up all the good stuff, the essential nutrients like phosphorus and calcium, basically starving the plant. And second, it can release toxic elements like aluminum, which is like a direct poison to the plant's roots. So where does all this acid come from? It's a mix, really. Some natural, some man-made. In places that get a ton of rain, essential compounds can literally just get washed or leached right out of the soil. But we contribute too, often with the very fertilizers we're using to try and help the crops grow in the first place.
All right, now for a totally different kind of problem. We're going from too much acid to too much salt. Yeah, it might sound a little strange, but having way too much of certain minerals can be just as destructive. It can turn fertile land into a salty, barren desert.
These salts can come from the natural weathering of rocks over a long, long time. But you guessed it, human activity plays a huge role here too. Irrigating crops with water that has even a little bit of salt in it can, over the years, lead to a massive buildup. This is especially true in dry, arid climates, where water evaporates from the surface and leaves all those salts behind, just building up more and more over time.
Now, salt-affected isn't a single diagnosis. You've got to distinguish between two main types, as you can see here. On the left, you have saline soils. Think of these as just generally salty. Their pH is below 8.5, and we measure the total salt content using something called electrical conductivity, or EC. But on the right, you've got sodic soils. And these are the really destructive ones. Why? Because they're dominated specifically by sodium. We measure this with the exchangeable sodium percentage, or ESP. When that ESP number gets high, the sodium literally breaks down the soil structure, making it dense and hard like a brick, completely unable to absorb water. That's what makes them such a massive challenge to fix.
Okay, so we've diagnosed the problems, right? Acid and salt. So what's the cure? This brings us to the most hopeful part of our story, the science of reclamation. It's all about healing these damaged soils.
I really love this quote because it just captures the spirit of this work so perfectly. We're not just trying to tweak the chemistry. The goal is to fundamentally restore the soil's ability to support a thriving ecosystem, to bring back that potential for life. So the path to recovery usually involves three main strategies, and you can use them alone or mix them together. We've got mechanical methods, chemical methods, and biological methods, basically using physical force, some targeted chemistry, and the power of life itself. First up, the mechanical approach. This is often the critical first step, especially in those really tough sodic soils, where the structure is just completely wrecked. Things like deep plowing or subsoiling physically break up those dense, impermeable layers. It opens up pathways for water to finally drain through the soil, which is absolutely crucial for flushing out all those excess salts. Next up, we've got chemical solutions, which are all about correcting imbalances. For those acidic soils, the answer is usually adding liming materials. Think of it as finely ground calcium carbonate. It works just like taking an antacid. It neutralizes the excess acid. For the sodic soils, the magic ingredient is often gypsum. Gypsum adds calcium, which kicks that harmful sodium off the soil particles, allowing it to finally be washed away. And finally, we have biological amelioration, which is all about using life to heal. This can mean planting special salt-tolerant crops that can actually survive in these tough conditions and help improve the soil. It also means adding lots of organic matter, like crop leftovers or manure. This stuff not only adds nutrients, but it helps rebuild the soil structure and encourages all those beneficial microbes that are really the lifeblood of any healthy soil.
So, here's the most important takeaway from all this. Land that seems dead is rarely a lost cause. Whether the problem is too much acid or too much salt, we have the scientific tools to figure out exactly what's wrong and how to fix it. With a smart combination of these mechanical, chemical, and biological strategies, we can absolutely restore these soils and bring them back to life.
And that leaves us with one final, really critical question. As our global population keeps growing and the demand for food just goes up and up, making every single acre of farmland productive becomes more vital than ever. So the question isn't really whether we can reclaim these soils, it's whether we can possibly afford not to.
All right, let's dig in. Today, we're going to get into a story that's happening literally right under our feet, but it's a story that's billions of years in the making. We're talking about the biography of soil, this absolutely incredible tale of how solid rock transforms into the living, breathing resource that, well, sustains all of us.
I mean, have you ever really stopped and wondered? Because it's not just dirt, you know? Every single handful has its own history, a family tree that stretches back through these mind-boggling stretches of time. It's this amazing story where geology, chemistry, and biology all just smash together to create something totally new.
And that's exactly what we're going to unpack. We're going to see how solid rock gets systematically broken down, piece by piece, only to be built back up into something completely different, something vibrant and alive. And this is not a quick process, not at all. It's a saga, really, written in stone and time.
Okay, so where does a story like this even begin? Well, like any good biography, it starts with the family. For soil, that family history kicks off with what scientists call the parent material.
Just think of this as the raw ingredient. You know, you can't bake a cake without the flour, right? Well, for soil, the flour is the rock and mineral matter it originally came from. This is the starting block, the ancestor from which every single type of soil descends.
So you've basically got three main family lines for soil. First, you've got igneous rocks, born from fire and cooling magma, things like granite. Then you have sedimentary rocks, which are basically recycled history. They're just little bits of other rocks all cemented together over time, like sandstone. And finally, metamorphic rocks, which are older rocks that got totally transformed by insane heat and pressure deep in the earth, like marble. Each one of these gives the soil that comes from it a completely different starting point, a unique set of genes for its life story.
So you have these massive, solid rocks. How in the world do they become soil? Well, that's where the next chapter begins, this relentless process of breakdown called weathering. This is where the action really starts to pick up.
Now, weathering isn't just one thing. It's more like a relentless, three-pronged attack. First up, you have the heavy hitters, the physical forces. Think of water getting into cracks, freezing, and acting like a wedge, just splitting the rock apart. Or even just wild temperature swings causing the rock's surface to peel off like an onion. Then you have this silent, sneaky attack, chemical weathering, where water and air slowly dissolve and literally change the rock's chemistry. And finally, life itself gets in on the action. Plant roots muscling into tiny crevices, little microorganisms releasing acids that eat away at the rock. It's just this constant, powerful assault from all sides.
And this quote, this just nails the real magic of weathering.
You see, it isn't just about destruction, it is profoundly creative. Yeah, it shatters solid rock, but in that process, it's actually creating brand new minerals and the raw building blocks for soil. It's both an end and a new beginning, all at once.
So we've gone from solid rock to basically a pile of rock dust. How does that become actual soil? Well, now we've got to look at the recipe that turns those little fragments into a complex living thing.
Now take a look at this. An ideal, healthy soil is so much more than just solid stuff. Sure, about 45% is mineral matter, that weathered rock we've been talking about. But here's the wild part. Fully half of a healthy soil is actually empty space. It's filled with the water and air that are absolutely critical for anything to grow. And then there's that last crucial 5%.
And that 5% is the secret ingredient. It is the game changer. It's life itself. The remains of plants, animals, microbes, all this organic matter is what turns sterile rock dust into a dynamic, living ecosystem. It's the spark that turns geology into biology.
Okay, so once soil starts to form, it does something amazing. It starts recording its own history. Over centuries, these really distinct layers start to develop, creating what's called a soil profile. And for a soil scientist, reading this profile is like reading the chapters of a book. It tells the complete story of that soil's entire life.
But hey, before we can read those chapters, we have to understand the language the book is written in. And that language is soil texture. It's really just the mix of different sized mineral particles, sand, silt, and clay. This simple mix pretty much dictates everything about how a soil is going to behave, from how it holds water to what nutrients it can offer plants.
And this chart just gives you a sense of how vast the difference in size really is. On one end, you've got sand grains. They're giants in this world. You can literally see and feel them individually. But on the other end, you have clay particles, which are microscopic. They're so tiny they act in a completely different way, feeling smooth and sticky when they get wet. The specific recipe of these three is what gives every single soil its own unique personality.
All right, let's actually read the chapters of this biography, The Soil Horizons. We start right at the surface with the O horizon, which is like the book's cover, just a layer of organic stuff like fallen leaves. Just below that, you've got the A horizon, or topsoil. This is the bustling first chapter, where most of the life and action happens. As water trickles down, it kind of filters things, pulling minerals out of the E horizon and dropping them off deeper down in the B horizon, the subsoil. Go even deeper and you hit the C horizon. This is like reading the early drafts. It's mostly weathered rock, a clear link back to the soil's origins. And finally, way at the bottom is the R horizon, solid bedrock, the very first page where this whole story began.
So we've journeyed from a solid chunk of rock to this incredibly complex, layered system. A cool story for sure. But why does any of this ancient history matter to us? Right here, right now? Well, the answer is pretty much everything.
The numbers you see here, that's time. Hundreds to millions of years. That's how long it can take to form a single, mature, working soil profile. This whole thing operates on a geological timescale, something way beyond a human lifetime. And that means, for all practical purposes, the soil we have, it's a non-renewable resource.
And that, right there, is the ultimate takeaway. This incredibly slow biography isn't just some abstract geology lesson. It's the story of the very foundation of our food systems, our ecosystems, our world. Once you understand where soil comes from, you realize just how precious and, honestly, how alarmingly fragile it really is.
So, as we stand on this ground that has been thousands, even millions of years in the making, the question we're left with is a simple one, but it's profound. Now that we know its incredible story, what are we going to do to make sure that story continues for the millennia to come?
You know, have you ever really stopped to think about the universe that's just teeming with life right under our feet? It's so much more than just dirt. It's this dynamic, living ecosystem, a whole hidden world that literally powers our entire planet. So today, we're going to dig in and really get to the heart of this world, something called soil organic matter.
All right, so here's how we're going to break it all down. First, we'll lay the groundwork and talk about the foundation of living soil. Then, we get to meet the incredible microscopic recycling crew that keeps the whole system running. After that, we'll have to look at the serious threats this hidden world is up against. And finally, we'll wrap up by exploring some really amazing ways we're learning to clean up the mess.
So what's the magic ingredient?
What is it that separates dead, lifeless dust from vibrant, rich soil that can support life? That very question, well, that's the key to everything we're about to get into. Okay, let's start at the beginning with the absolute foundation. We're going to unpack the essential ingredients that make soil healthy, fertile, and, well, alive. And this brings us to a really crucial concept. It's called soil organic matter, or SOM for short. Now, the key thing to get here is that SOM isn't just one thing. It's this super complex mix. I want you to think of it as the legacy of all the life that came before. Every plant, every animal, every microbe, all breaking down to become the lifeblood of the soil. It is, quite literally, the living, breathing heart of the ecosystem.
So what's actually in this organic matter? Well, it's a rich cocktail, really. You've got your simple stuff, like sugars and amino acids, which are like fast food for microbes. Then you've got the tougher materials, like cellulose from plant walls, and proteins. There are also fats and waxes in the mix. And then the really, really tough stuff, that woody material called lignin. And of course, all of this is packed with vital elements like sulfur and phosphorus. It's basically a fully stocked pantry for the entire soil food web.
But here's the thing. The amount of this precious organic matter isn't the same everywhere you go. It's shaped by a bunch of different factors. Climate is a huge one. Warm, wet conditions can really speed up decomposition. The kind of plants that grow there matter too. For instance, grasslands tend to build up a lot more organic matter than forests. Even the texture of the soil plays a part. Tiny clay particles can actually shield organic matter, protecting it from being broken down. And, this is a big one, human activity like tilling a field can cause SOM to plummet by exposing it to the air.
So we've got a handle on what organic matter is, but now, how does it all happen? To understand that, we need to meet the hardest working and probably most underappreciated workforce on the entire planet, nature's recycling crew. And this crew's number one job? It's decomposition. You can think of this as nature's ultimate recycling program. It's the process where all that complex stuff we just talked about, the dead leaves, roots, you name it, gets broken down into simple, basic nutrients that new plants can soak up and use to grow. It's the circle of life, happening on a scale you can't even see. Now, this breakdown process happens in a few stages. The crew doesn't just dive in and eat everything at once. No, they start with the easy stuff, the fast food of the soil world, like sugars. Once that's all gone, they move on to the more complex meals like cellulose. And then finally, the specialist crews show up to tackle the toughest material of all, that super strong woody lignin.
Okay, so while all this is going on, there's this fascinating tug-of-war happening over the nutrients. On one hand, you have mineralization. That's when the microbes release nutrients in a form that plants can slurp right up. Think of it like putting cash into the economy for plants to spend. But at the exact same time, you have immobilization. That's when those very same microbes are using the nutrients for themselves to grow and multiply. They're basically taking that cash and putting it in the bank for a while, and a truly healthy soil is all about maintaining that perfect balance.
So who exactly are these amazing recyclers? Well, first up, we have the undisputed champions of the soil world, bacteria. These guys are the primary decomposers, the real workhorses. These tiny, single-celled powerhouses are absolutely everywhere, and they do the vast majority of the heavy lifting when it comes to breaking down organic matter.
Next, let's meet the specialists, fungi. Now, while bacteria are handling the bulk of the work, fungi, with their amazing network of thread-like hyphae, are the true masters of breaking down the really, really tough stuff. They're like the heavy-duty demolition crew that can take on things like wood and lignin that bacteria just can't handle.
And finally, we have the finishers, the actinomycetes. These are just fascinating organisms. They really shine in the later stages of decomposition, helping create that stable, rich humus. And here's a really cool little fact for you. They're the ones that produce a compound called geosmin. That's what gives soil that wonderful, classic, earthy smell after it rains or when you till a garden.
So, this whole intricate living system is incredibly powerful, but it's also pretty fragile. And that brings us to our next section, a world under threat. Because we really need to talk about how human activity, and pollution in particular, is putting this entire microscopic world in serious danger. So, what do we even mean by soil pollution? Well, basically, it's when toxic chemicals or other nasty contaminants build up in the soil. And they build up to a point where they become a direct risk, not just to the little organisms living in the soil, but to the entire ecosystem. And that includes our own health.
And where is all this pollution coming from?
Well, unfortunately, the sources are all around us. You've got waste from industrial plants, sewage and garbage from our cities, and agricultural runoff from things like fertilizers and pesticides. Even things you might not think about, like excess salt from irrigation systems, and, of course, all the plastic we throw away. It's a huge problem.
And the specific villains in the story are probably what you'd expect. Pesticides, right? They're designed to kill things, and they don't always stop at the target pest. Excess fertilizers can leach into our groundwater. Heavy metals like lead and mercury from industry are incredibly toxic, and they stick around for a long, long time. And of course, plastics are becoming a massive menace, breaking down into tiny microplastics that just wreak havoc on the soil environment.
Now that all sounds pretty grim, I know, but it's not hopeless. And that brings us to our final section, which is a much more hopeful one. We're developing some incredible techniques for actually cleaning up this mess and healing our soils. This is the amazing field of soil remediation.
One really cool method is called air sparging. This is what you use when pollutants have sunk way down into the groundwater. You basically inject air below the contaminated spot. This forces the volatile chemicals to turn into a gas, bubble up through the soil, and then you can collect them at the surface. It's almost like you're blowing bubbles to clean the earth from the inside out.
Then you have something called soil washing. And yeah, it is pretty much exactly what it sounds like. You literally dig up the contaminated soil, you put it in a machine, and you wash it with special liquids that scrub the pollutants right off the soil particles. The clean soil goes back, and the now contaminated water gets treated separately.
And this next one brings us right back to the beginning. Biopile treatment actually uses the power of that microscopic recycling crew we met earlier. You dig up the contaminated soil, you pile it up, and then you add nutrients and pump in air. You're basically creating the perfect environment to supercharge the native bacteria and fungi, helping them do what they do best, eat and break down the pollutants, completely naturally.
A similar but more large-scale approach is called land farming. With this method, you spread the contaminated soil out in a thin layer, and then you just till it regularly. It's a lot like turning a compost pile. All that tilling mixes in oxygen, which encourages the soil's natural microbial community to get to work and degrade those contaminants over time.
So, what a journey, right? We've gone from the very building blocks of soil, to the incredible microscopic crew that makes it all work, to the very real threats it's facing, and then to some of the amazing ways we can actually heal it. And that brings us to one final, really important question. This vast, complex, absolutely vital world beneath our feet is what sustains all life above ground. Everything. So we have to ask, are we really doing enough to protect it?